if we have a diffraction grating with 2 openings or 3 openings or 1,000 openings, it doesn't really matter. Light will pass through those openings, diffract around each of those openings, interfere, and produce an interference pattern. Now, if we introduce a screen up here to detect that interference pattern, the interference pattern is pretty predictable. We should see right directly above those 2 openings or above those 1,000 openings or whatever, an area of constructive interference that we call a maximum. In other words, we see a bright spot. 2 crests have to come together or 2 troughs have to come together to form a bright spot, a maximum. And beside that, though, we get an area of destructive interference where we usually call it a dark spot or a minimum, but it doesn't really mean that it's dark. It's just the absence of bright. Like, it's not darker there than it would otherwise be. It's just not brighter there than it would otherwise be. So we call it a dark spot. And then next to that, we get a bright spot again, which is an area of constructive interference, and then a dark spot, and then a bright spot, and so on and so on and so on. We get these alternating areas of bright spots and dark spots. That's our interference pattern. Now, that middle bright spot, or that middle maximum, we're going to call our central maximum, and we're going to assign a number of 0 to it. Okay, it's maximum number 0. Bright spot number 0. Constructive interference spot number 0. Right next to that, on either side, you're going to get your first order maximum. We're going to assign a number of 1 to that. And then second order maximum, and third order maximum, and fourth order maximum, and so on and so on and so on. Now, in between that, we have our minima, or our dark spots, or our areas of destructive interference. We're going to assign numbers for that are half numbers. Not 0, 1, 2, but rather 0.5, 1.5, 2.5, 3.5, and so on. So the third order maximum would be number 3. The third order minimum would be 2.5, because it's the third one from the central maximum is 2.5. On the other side, same thing. I'm not going to write those in because it's going to look a little cluttered pretty quick here. But we get the same numbers on the other side. It's always symmetrical from one side to another. Now on Friday, the day that I wasn't here, when you watched the podcast, you learned 2 equations that had a number of variables in them that can be drawn on this diagram right here. The most confusing thing about these problems, I think, is keeping the variables straight. Like, there's so many variables that you got to keep straight. And that, I think, more than the use of the equations themselves, is the more challenging thing. We're going to label this distance between the slits as a little d. We're going to label this, that's the distance from the slits to the screen, as an L. Whether you call it a lowercase l, capital L, doesn't really matter. On your data sheet, it's a lowercase. Yeah, I'm going to write it as a capital L here just because it's going to look like a 1 if I write it as a lowercase l. Now, x, this is a confusing one. People are, that doesn't make any sense. When I say that x can be measured from, I don't know, the second max to the fourth max, or I say that x can be measured from the first max to the fourth minimum, or from any other maximum to any other minimum. You look at it and say, Mason says, well, how is it that I can make mine from the second max to the fourth max, but Zach can make his from the first max to the third min, and yet we get the same answer? Well, you can make x whatever you want according to what's given to you, as long as the value of n is consistent with that. N is a number that is just a difference between the maximum or minimum number. So when we're going from second max to fourth max, we're going to say n is equal to 2. 4 minus 2 is 2. When we're going from the first max to the fourth min, we're going to say n is going to be equal to 2.5, right? 3.5 minus 1. Just subtract the max/min number, and that gives you the value of n. And x can be whatever you want as long as n is consistent with that. Now, the other one that we have is theta. X can be measured from anything to anything else. Theta is close. Theta can be measured to whatever we want, whatever max, whatever min we want, but it always has to be measured from the central. So x from whatever to whatever, theta is from the central to the fourth order max, or from the central to the second order min. We're going from central to fourth order max. N will be 4, right? From 0 to 4, 4 minus 0 is 4. If we're going from central to the second order minimum, then N would be 1.5. From 0 to 1.5 is 1.5. So theta from central to whatever, x from whatever to whatever. And as long as N is consistent with those, doesn't really matter what it is. Whatever it is that's given to you is what you use. Now, we have two equations that use these variables. Like the first one, that's the one we want to use because this is the one that's always valid. Lambda is equal to d sine theta over n. We already know what each of these variables mean. Okay, this equation is valid no matter what. We'll put a check mark by it because you can use it whatever the circumstances, as long as theta, that is measured from the central maximum. That second equation that I gave you on Friday, lambda is equal to xd over n times L. This is oftentimes a more convenient one to use. We're going to want to use this fairly often. But we're going to star it because it's only valid if theta is less than 10 degrees. I mean, the reality is it's an approximation all the time. But it's a very good approximation if theta is less than 10 degrees. The number that you get from this will work out to be a very, very, very good number if theta is smaller than 10. But it's not perfect. The problem is, above 10 degrees, it ends up being like way less than perfect. So the rule of thumb is that we can use it if it's less than 10 degrees, but if it's bigger than 10 degrees, don't use it. Don't go there. Now, we did create a rule of thumb on Friday. A rule of thumb, or a ROT, that allows us to not necessarily calculate the angle every time. If we get a question, we got to check to see if it's valid, to see if theta is less than 10 degrees. It means you got to calculate theta every time. I'm not asking you to do that. I'm asking you to use the rule of thumb. The rule of thumb is this. If L is greater than 10 times x, then we can say, yeah, it's valid. Now, this little rule of thumb that we have errs on the side of caution. There's going to be the odd time when you find that L is not greater than 10 times x. You calculate the angle and you say, oh, wait, theta is still less than 10 degrees. Oh, well. You'll never find the other way, though. You'll never find L is not greater than 10 times x. Or you'll never find that L is greater than 10 times x, and then learn later on, oh, I can't use the equation. If L is greater than 10 times x, 100% of the time, you'll be able to use that equation. Theta will always be below 10 degrees if L is greater than 10 times x. So every time you look at your givens and you want to use this equation, do the little rule of thumb check. If L is greater than 10 times x, good to go. If it's not greater than 10 times x, then find theta, and if it's less than 10 degrees, you can still use this. But if it's not less than 10 degrees, then you've got to use this form of this equation or some form of that equation. Let's take a look at question number 5 on your worksheet. It says, light with a frequency of 5.5 times 10 to the 14 hertz is shone on a diffraction grating scored with 6,000 lines per meter. Distance between the slits and the screen is 2.5. What's the distance between the second order max and the fourth order maximum here? Whew, this is a tough question. Good choice. Good choice on questions to go over here. First of all, we have a frequency of 5.5 times 10 to the 14. We don't want that. None of our equations here have frequency in it. We want to get from that wavelength. Okay, we'll see how to do that in just a couple minutes, but we know we're going to want wavelength from that. Now, we've also got 6,000 lines per meter. That's 1 over d. But we don't want 1 over d. We want d. D is the equivalent of meters per line. 1 over d is lines per meter. So we're going to have to convert that as well. The distance from the slits to the screen is 2.5. That's going to be L. We want the distance from the second maximum to the fourth maximum, so we want x. Let's draw this out here. Central maximum, first, second, third, fourth. The distance from the second to the fourth maximum is, well, n is going to be equal to what? The difference between 2 and 4 is 2. So n is going to be equal to 2 here. All right, let's get the wavelength here. We could say wavelength is c over lambda, which is 3 times 10 to the 8 meters per second, divided by c over f, I should say, divided by 5.5 times 10 to the 14. That gives us a value here for the wavelength of 2.5 meters. Is that what you guys got? 2.5 meters? Is that what you guys got? Thank you. That is wrong. 5.45. It didn't look right. And sure enough, it isn't. 5.4545 times 10 to the negative 7 meters. Now, D, we can find by just flipping over the 6,000. So 1 over 6,000 gives me a value of 1.66667 times 10 to the negative 4 meters. So now I've got lambda and I've got D. I want to solve for x. I'm going to say lambda is equal to xd over n times L. Rearrange that to solve for x. I get lambda n L over d. Now, this is a good question. It maybe isn't the greatest one to start off with because we want to use this equation. We normally want to do our check, right? Is L greater than 10 times x? We can't do our check here because we don't know what x is. We just have to trust that it's valid. If you ever come across a situation like this, we have to solve for x. I think it's safe to assume that it's going to be a valid equation. I wouldn't worry too much about that at that point. So we're going to sub in our numbers here. Lambda is, we just found it, it's 5.45 times 10 to the negative 7 times n, which is 2, times L, which is 2.50, divided by the distance that we just calculated a minute ago, 1.6667. We get a value for x of 1.64 times 10 to the negative 2 meters. The other one that we wanted to go over was question number 4, so let's take a look at that now. Because light of wavelength 530 nanometers, that's going to be a wavelength of 530 times 10 to the minus 9 meters. The distance between the slits, we want to find the distance between the slits, little d. The angle from the central max to the second max is 16 degrees. The angle from the central maximum to the second order minimum. Central maximum to the second order minimum. What would n be there? 2? What's n? 2? What is it doing? 1.5, right? Going from 0 to 1.5, we're going to say n is 1.5. Now, we don't have to do any check on this one. Clearly, the angle here is bigger than 10 degrees. We're given the angle, so we might as well just use the one that we know is always valid. Lambda is equal to d sine theta over n. This one just always works. Looking for d here. So let's take the n up by multiplying. And then let's take the sine theta down by dividing. Lambda times n over sine theta. Make sure you're in degree mode on your calculators. 530 times 10 to the minus 9 times n, which is 1.5, divided by sine 16.0 degrees. You get a value here of 2.88 times 10 to the negative 6 meters.